So Calculus Lesson 1.2 continued. Example 5. We need to find the limit as x approaches negative 6 for the function drawn to our right, and also find the value of f of negative 6. The limit as x approaches negative 6. So I'm going to go here to the graph where x is negative 6. The limit, that means what is the y approaching when x gets close to this, from the right and the left side? See, that y value right there is 2, from the right and from the left. So this limit would be 2. The value, when x equals negative 6, that y value is actually 2. So this answer would be 2 as well. All right, the next one would be at negative 4. So let's go to x equals negative 4. 1, 2, 3, 4, negative 4 right here. The limit, well, wait a minute. At x equals negative 4, on the left side of my graph, it's going down. It's going to negative infinity. The right side of my graph, it is going up to positive infinity. So this limit as x approaches negative 4 would not exist. They are not the same value from the right and the left. What about the value of the function at x equals negative 4? Is there a y value for this when x equals negative 4? See, no, there's not. This is a vertical asymptote at x equals negative 4. So the value for f of negative 4 would not exist. Oh, and D and E in calculus means does not exist. All right, at x equals 0. The limit is x equals 0. So here's the line x equals 0. From the left, that answer would be positive 1. From the right, that answer would be negative 2. Because they're not the same, this limit does not exist. But f of 0 does exist. See, what is the y value when x is 0? So right here where x is 0, that y value is negative 2. That is a closed-in circle. So that would be negative 2. And again, for this limit to exist, it had to be the same from the right and the left. So here was x equals 0. The left side of it was 1. X equals 0. On the right side, that y value was negative 2. These were not the same. That's why this did not exist. All right, next we're going to do a 2. X equals 2. So right here, when x equals 2, from the right side of the, from the left side of the graph, that y value is approaching 3. From the right side of 2, that y value is also approaching 3. So this limit would be 3. But the value at f of 2. See, when x equals 2, is there a y value? No, there's not. That's an open circle on the graph. So the f of 2 doesn't exist. And the last one for this example was at x equals 4. So again, when x equals 4, the y value here from the left side is approaching y is 2. From the right side, the y value is also approaching y is 2. If I asked you for f of 4, when x equals 4, what is the y equal? That would be this 4 right here from that closed dot. So again, this open circle right here was from my limit from the right and the left. Both of those were 2, so therefore this first answer was 2. F of 4, when x is 4, y in this case happened to be 4 as well. So the different types of limits that are non-existent. So if you have a different number from the right and the left, the limit doesn't exist. When f of x increases or decreases without bound, those was the ones when I discussed the positive or negative infinity. It also doesn't exist if it oscillates between two numbers. So the formal definition of a limit. It says the first person to assign mathematically rigorous meanings to these two phrases was Augustin Louis Cauchy. His epsilon minus delta definition of a limit is the standard used today. So basically what's happening here is we're saying this limit as x approaches c. We're going a little distance out from it, a delta. What is that y value getting really close to as this x value here gets really close to c? So we had a small amount to this right and this left. We had a small amount to this y's and this right here. And that's what we would be saying that's the limit. We don't do a whole lot of this with the formal definition. I just want you to see it. You may end up in Calculus 2, and you may end up needing to use this formal definition in that course. So using this formal definition, it's telling me let function be defined in an open interval containing c, be a real number. The statement the limit as x approaches c of f of x equals the capital L means that for each epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than x minus c, that's the value of that, less than my delta. Then the function, f of x minus the limit, would be less than epsilon. So there's a couple problems in the homework where we have to find our limit, then we have to find the delta. So we're just going to plug into our function. First, let's answer what's this limit. See, this would be the equation of a line. 2x minus 5 is a line. That's smooth, it's continuous. So at x equals 3, I know that y value is going to be the same from the right and the left. So we can just plug 3 into this. That gives me 6 minus 5, which is 1. So my capital L is a 1. F of x, that's the 2x minus 5. L, that was the 1. C, that's this number right here. The limit as x approaches 3. So I'm going to put that C right there. We're going to come back to this one in a minute. We need to work this problem first. So this was the opposite value of 2x minus 6 was less than 100th. See, that would mean 2x minus 6 is between negative 100th and positive 100th. Add 6 to both sides. Divide both sides by 2. Now what we're looking for is how far off are each of those x's, this down here, from 3. See, this would be 3 plus tenths, hundredths, thousandths. 3 plus 5 thousandths. This would be the 3 minus 5 thousandths. So therefore, that has to be 5 thousandths for this. Whoops, I hit the wrong key, sorry. So therefore, my delta has to be the 5 thousandths. Again, I was looking for how far off of 3 are both of those, because I want that to be an x minus 3. That ends lesson 1.2. If you would be able to do the multiples of 4 and 15 by the time you come to class, that'll let us know which ones I need to go back over for reteaching. Thank you.